So we're starting from the introduction. Hopefully we can finish today. We start from Euler's formula. So this one is we say is bridging between the complex domain to axis in complex axis. And we briefly talk about why we need Euler's formula for Fourier and Laplace transform, and what is the symbol we are using: discrete time, continuous time, time domain, frequent domain, and talk about some system, and talk about continuous and discrete time, time shift, reflection, time reversal, time scaling. They are scaling by time. Also define the what is function of periodic signal. Periodic signal is we define as a set of signal repeating by a certain time. And we have even and odd function, symmetric around the y-axis, symmetric around the origin. And we also cover the complex exponential signal. In the case of simplest case, both C and A is real. When A is imaginary, and both C and A are imaginary. And the final thing is we have exponential as a kind of envelope, and we have a sine wave oscillating between those exponential signals. Also, we define what is a step function, a unit step function. Unit step function is they become 1 after the value n is larger or equal to 0. Delta function is an impulse at 0. They only 1 or infinity at 0. Other than that, they are 0. Because it's hard to define the derivation, it's like mathematical, that's not right. So we define them in the way that we have very small value delta and make delta to 0 to define the delta function. So today we start system. So system we can define likewise many things. There are continuous time system. Input is continuous signal, output is continuous signal, and as input and output are continuous signal y, x, t, so the system will be continuous system. If input is discrete and output is discrete, often we have discrete time system. So both of them looks like a box, but they're actually a different system. Sometimes we'll cover it briefly in a sampling section in later chapter. Sometimes they are cascaded, meaning that sometimes we have input of continuous time passing through continuous system, and then after that we do something called sampling. Sampling is what? We pick up some value at a certain period of time. So assume that we have continuous time signal, we pick up value at a certain period of time, meaning that we change the continuous time to discrete time signal. So after passing through the sampling, this continuous time system, a signal will change to discrete time signal. And this discrete time signal can go back to discrete time system, pass through, and discrete time signal will come out, and we can change it back to continuous time. So let's briefly talk about that. Of course, we'll cover in later chapter, but let's briefly have a taste. So I say we have a continuous time system, a signal like this. After passing through something called sampling, we will have a discrete time, meaning that we pick up values at equal period and make a set of discrete time signal. So we change continuous to discrete time likewise. How we can go back to here? How we can go back to here? There are several ways we can do it. So one way is we can do the interpolation. Interpolation is what? We have, I think you already learned in high school. So assume that you have this value and this value in time domain. How we can assume, how we can estimate the value at here, at this time? Right. So we pick up, assuming that they are linear in here, and pick up an average value between those two. That's the simplest way. Or we can do many things. We can assume that there is, okay, so assume that there is a power of 2 relation between them. We can assume like that. Or what you can do is something called sample and hold. We say sample and hold it until next value. Okay? So we hold, 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 so that they can be, looks like something like this, right? So there's many ways you can do it. So this is a very common system you can find in many engineering systems, especially telecommunication system. So many signal itself coming from the nature is analog, right? They are continuous time. We have to convert them to continuous discrete time system or a discrete value by using sampling value like data acquisition system to be used in computer. We do the processing in a computer in a discrete time, and then we have to change it back to the continuous time. Think about the example I used in the first day of lecture. We used music, right? In case of music, it's coming from computer. There's discrete time signal, right? And it should convert to continuous time to be here, to be heard in your ear, right? So that's one example that they can be go back and forth continuous time. Of course, we are losing information because this one, this yellow one and this white one is not exactly the same. There's some chance that in here we assume that they are linear, but actually this is not linear. They are like a little bit shaped, right? So we are losing some data always. We always lose the data when you convert the information. However, we try to make it as close as possible using minimum resources. That's one of objective in signalization systems. Anyways, we have input and output will be the same. We can have continuous and discrete time. And sometimes we call something called CISO, single input, single output. This is CISO system, single input, one output. You may hear MIMO in telecommunication a lot. MIMO means multi-input, multi-output. So more than one input, there's only one input here. There's more than one input coming from the system, coming to the system, more than one output coming out of the system. That's called MIMO. So how they are connected is we can divide them several cases. First case is series, cascaded, meaning that they are one system and second system is connected in series. So input should pass through each system. They have to pass through every system until they come to as output. So this one called series because this is series connected and we have to pass through all the system until we reach the output. Parallel system is a little bit different. Parallel system, we can process them together at the same time. So when there is input, we have system 1, system 2, they goes as a parallel. We don't have to wait system 1. System 2 don't have to wait system 1. In here, system 2 should wait system 1, right? Because this output of system 1 becomes the input of system 2. In here, they do not, because system 2 does not have to wait the output of system 1 because they are working as an individual, working individually. And their output will combine maybe minus, and output come out. This is parallel system. We can have both of them because in here, this one is parallel, right? But in this line, they can be series or cascaded. So we can have a combination of two. And this whole system and this system 4 are cascaded, right? So sometimes we define them like this. Let's say the transfer function of system 1 as Hs. The transfer function of system 2 is H12, let's say like this. If they are cascaded, how we can find the system function of all of these? You already learned from the control lecture or previous like the electronic lecture how we can define them. Simplest way we can see it is a filter. You may hear that we have one filter like this, and you can have another filter. Right? That's one example. So here, this system, we assume that their cutoff frequency is 10 Hz. In here, our second system, we have cutoff frequency of 5 Hz. Okay? So the signal should come in, pass through the first filter, they're filtered out with the filter frequency here, and this output become input to the second filter, and the final output will be filtered in 5 Hz. So this is one example we can have a parallel system or cascade system. And how we can define their transfer function? We usually define them as multiplication of these two because they are cascaded. Let's have one example. We often have this low-pass filter. I'm not sure this low-pass or high-pass filter. I'm not sure about it. However, assume that H1 is S times omega, too much, A over 1. H2 second transfer function is given like this. Assume that we like that. If they are cascaded like this, the input should come to here, and then output of this one become input over here. So they should be multiplied. So the total transfer function will looks like this. If they are looked as a parallel, input to the system is divided into two. Say that input 1, input 2, right? And output 1 and output 2 will come out. Too fast? No? So this one, H is what? H1 is what? You learn that H function is a relation between input and output, right? So input is what? I1. Output is what? O1, right? H2 is what in here? What is their input? I1, I2. Oh, okay. And output is what? O2, right? And in here, right there, we add an adder. We add them, so final output will be output 1 plus output 2. Right? And then in here, output 1 is what? H1 times I1 plus output 2 is what? H2 times I2. As in here we have one common rule. If they are connected without adder, without minus or whatever, no multiplier, they have the same signal. So this I will go to here, this I also go to here, meaning that I1 equals I2 equals input. So this I becomes H1 times I plus H2 times I, meaning that H1 plus H2 times I. So the relationship between input and output in the whole system will be plus this. Very simple proof, but we will tell you that. How about the cascade case? In the cascade case, assume that we have input, say this is output 1, say this is output 2, right? So S1 defines input and output. So H1 equals I over output 1. H2 defines input is output of S1. So output 1 over output 2, like this. What we want to have is input is I, output is output 2 in whole system. To get it, we simply multiply them, because when you multiply them, this output will be cancelled out. So left over is output 1 times output 2. So in cascade system, we define the whole system transfer function or whole system function as multiplication of each system. In parallel, we add the system function of each system. That's how we do it. So let's change the question to like this. Let's have an example. Is it clear? Question? If you are asked what is the system function of all of these, 1, 2, 3, 4, how do it? So let's segmentize it. We have system 1, system 2, system 3, system 4, and that's the output. And we have adder here. So let's segmentize it. Here is what? Here is cascade. Here is cascade, right? So transfer function in this yellow box is H1 times H2. Right? And what about the system function in here? We have this one as this one, H1, H2, and H3 are parallel, and they are added. So we should add them. So H1, H2 plus H3 will be transfer function in this solid line. What about the system function covering all over here. This box has transfer function like this. This box and number 4 are cascaded, right? They're cascaded. So how we do it? In cascaded, we multiply them. So this one and H4 are multiplied. So this is the system function describing the whole system. Quite simple. Not so difficult, hopefully. But we will use them in later chapter, especially chapter 6 or 7, I believe, when you design a system. Because when you design a system, for example, if you want to have vehicle system, sometimes you have engine. So you try to model all the system of the vehicle. For example, you have an energy source like a gas system. You have first the engine, you have a gearbox, you have a powertrain, and you have a wheel rotation system. Each system can be modeled individually. How to connect them? You should draw. So you should, one way to model a system is, model individual system, make a box of individual system from gas tank, engine, gearbox, powertrain, wheel system, rotation system, even the brake, and place them along the way that they are series or parallel. In case of from the gas to the engine, maybe they are cascaded, right? Without the gas, we cannot put on the engine, right? And then from the engine, we go to gearbox. In parallel, there is a brake system coming, right? Brake system don't have to go with the engine. So you can design them in the way. So this is a very simple approach, but very useful, because you can, if you want to model a big system, you segmentize into individual system, place them parallel series, and then find whole system. All right. Sometimes, so in here, we go from the input to the output, no coming back. Sometimes we need a feedback. Feedback means output go back to input. So let's have an example here. So feedback means previously we don't have this system. We just coming from input goes straight to the output without coming back. In here, feedback means sometimes output go to input. This is very important in control system, because in control system we want to monitor output. If output will be the same to the input, output is same to what we designed. So we keep on checking output, feedback to the input, and control the input so that we can adjust the output. That's how we use a feedback system. Example. Example will be set here. So let's have voltage, capacitor, and resistor. Capacitor, resistor as input. If you are asked, make a box, make a system box like this system over there, feedback, using this system. How you make a box from this system. So let's have this one is I1, this one as I2. Right? And say this is output. So this is just my way, so my method. You can have your own method. So I'm saying that this is not principle. This is one way I do it. first thing you do it is simply define what's the input, what's the output. So when you place it, you have some kind of big black box, right, in here. And you have input and output to the system. So let's define what is input, what is output. So in here, they are drawing I, T, right, according to drawing. And this goes to the system and V coming out from the system. So intuitively, we can think that, okay, this is input coming to the system. This is output coming out from the system. So we define them as input is IT, output is VT. We define them like this. Make sense? Okay. And how we can find out V? How we can find out V? So if you in the exam, or if you got a job and your boss say, okay, let's build a model in MATLAB to analyze this circuit. How do it? So let's define, first thing you have to do is what's the input, what's the output? Input, output. And let's think about how to connect input and output. So there's a lot of equation, but first let's think about the input. In input, they come in here and go to here, and they are divided. Now they are divided, right? Remember, previously in cascade, assuming we have a cascade case, they are go straight, no dividing. Even parallel, they are looks like divided, but I say they are actually the same because they are connected. But in here, they are divided into two cases. So we have to use plus or minus, right? If you use this one line, we cannot do it. So simplest way you can define here is IT equals I1T plus I2T. There's one equation we can define it. And we know that somewhere here we need a plus or minus. We have to divide it. And then we find another way we can divide, we can find output. We have to find a way to define output. Output V. How we can define output V? One way is here. Output V equals I2 times R. So R times I2. That's V, right? What's another way in here? Because voltage is the same, the voltage across here will be same to here. So how we can divide the voltage across here? We integrate I1T, make a Q, divide by C. That's the voltage. Right? There's two ways we can define it. Right? Question? No? Okay. So we just find out the way to bridge the input and output. Of course, this is not the input and output, but we can find the relationship between I1 to input I or I2 to I. How we do it? Assume that we have I1. Somehow we do that and find I1. So we come to here, come to there, and we need another path making I2T based on this relationship. Assume that this straight line is I1. What do we need? We need one box because I1 and output are related in the way like this. So we have integration of I1T divided by C. That the output of this box will be the V. Right? So we'll first build one line and think about how we handle this floated line, not connected line. How we handle it, we used first example. So the output are related in the way that output is related in the way that if you pass through the R, we can have the output. That's one way we can do it. Or, so we can build like this. That's one way you can do it. But we can design other ways. Because what to fill in this empty circle, is not so straightforward. Do you want to put an X? Do you want to put plus? Do you want to put minus? Why should we do it? Either way. So let's think about another way. Let's use a feedback. Let's do the feedback the other way. So we don't use it. Instead, we divide by R. Right? Then the output. So now this is input, this is output. Input is V, divided by R becomes IT, I to T. They go to here. Note this I is this plus this, but they have different direction. So to adjust the direction, what do we need? We need a minus. Because in here, this relationship is I1 minus this would be here. So in here, I minus I2 becomes I1T. Because this small circle is also a system. So this and this is input to the system. They're coming from different direction. If they're minus, we subtract them together and then find the output. So this is one way we can define our system. Of course, you can design them differently. That's what we've seen in here. This is what we just derived. Of course, we can do different way. Because assume that this is I2 instead of I1. Assume that we have this I2, right? Then how we define the output? Using this. So this box becomes R. I2 times R becomes V output, right? So that's one line you can make it. How we define the other way? We take the output, differentiate it to get I1T, right? And then we also do the minus because in here input is IT minus I1 becomes I2 as output. So this system and system on our slide are same system, describe the same system, but we can model them differently. We can model them either what we show in the slide. Straight line is capacitor, feedback is resistor, or you can use the other way. Straight line as a resistor, feedback is capacitor. So we can design either way. So even though what you can see in here is, even though you model the same system, you can model them differently. So if you find a way to simplify the model, you have a much easier analysis. Okay? Questions? Nope. Okay, let's move on. So now we're studying some definition. In property, previously we talked about the property of the signals. Now we talk about property of the system. We are talking about property of the box. Okay? So first one is memory. If you think about the memory, what's the image coming through your brain? If you think about a system has a memory, system can be your cell phone, system can be your album, so system can be anything. System have a memory, try to remember the past, right? So in the system with the memory, even though the definition is here, system with a memory means that we record the past. That's what it says. So if you define the memoryless system, so without memory, that is a system that output. Let me erase it. So we are talking about the property of the system. So we talk about the property of the system box we are using. So assume that we have an input or box of system, input, and output. In the memoryless means output is depending input at the same time. So we do not rely on the past. So sometimes we have a system that we have to know the past. For example, if you think about sport activity, sports athletics, they record their for example, you are a 100-meter sprinter, you record your every day. You record your record for running 100 meters, and keep on track it. That's a memory, right? In this system, memory system, they only rely on today, right now. So they are given like this. So example given here is YT like this. Output of the system, YT, depending on XT, input to the system at the same time, right? If we have similar, but like this. So to learn the time, the value at time of 0, we should know the time of -1. Let me rephrase it. To know the output at time of 0, we should know the input at time of -1. Time of -1 is past compared to 0. This one, we need a memory. This one, to know the output at time of 0, we need to know the input of when time of 0. We don't need to know time of -1, -2 past. So this one, we don't need a memory, memoryless system. This one, we need a memory, memory system. One example is like this. This one on the slide, this one is given to, okay. Given that this one need a memory. Why this one need a memory? Why this one need a memory? When you do the sigma, that means we are adding from -infinite plus blah 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 plus x n minus 1 plus xn. That's what it says. So this is current, but these are all the past, right? So because we need information of past to know the output or at current state. So this one is memory system with memory. This is how we define it. Memory is not so difficult, I think. Let's have a practical example. Let's have a practical example. Assume we have a circuit, we have resistor. Previous example, we described that what is input, what is the output. What is the input? Say there's input, there's a current, there's a current, this is input, and there's a voltage, which is the output. Right? Input to the system is current, output coming out of the system is a voltage. How we define the relationship is something times input, which is the resistor, right? This one is memoryless or memory. Memoryless, because output at time of 0 does not depends, only depends on time of 0 of the input. So this one don't need a memory. If you have say mod capacitor, how we define it? Output and input should be related. In here, we define integration, right? So intuitively, capacitor or inductor, they store the energy. So we can intuitively think that, okay, this one needs a memory. We can intuitively think. But mathematically, how we define it? Of course, you can define them as, all right, assume that integration of I is IT, and this one is some initial value to certain t, so IT from 0 to certain value. This original value, initial value is a past, right? This is not the time of t. They are past. This one is past of time of t. So we can think that, okay, we need the memory right away. Or we can differentiate it. To see that this. So we can also think them as like this. And then the differentiation is what? For small delta t, something like this. So to get this, we need to understand the past. That's another way we can think it. We can judge this one is the memory or not. So you can think there's another concept coming relating with the timing of the past and present. One way we can define memoryless or not is if this one only depend on current, or if we need the information from the past. Let me try that one first. There's a number 3. Let's pass through number 2 for a short time and go to causality first. Because this causality and memory has some coincidence, some corresponding part. Causality also talk about the timing. Causality means output at any time depends only on values of input at present and the past. No influence from the future information. So the difference from memory list and causality is memory list, we only, in memory case, to be memory list, they only depend on present. All right? So let's see. So we have past, present, and future. In case of memory, to be memory list, we only depend on present. In case of causality, we depend on present and the past. So causality, so you can think that, okay, system has a memory. If system is a memory list, that is automatically causal. Because memory list means only depends on present. And in case of causality, we only depend on past and present. We don't depend on the future. So memory list system automatically become causal system. Causal system cannot be automatically become memory list because causal system is also sometimes depend on the past. But memory system, we cannot depend on the past. That's a major difference. So let's go back to our example. We learned that this one is, we also need a memory. We just learned that this one needs a memory because it depends on the past. This one does not depend on the future because we only adding up to time of n. We only adding up to time of n. We don't have an input like xn plus 1 or xn plus 2. This one depends on the future, right? The future. This one has a memory because it depends on the past, it depends on the present, but not depending on the future. So this one is causal system. This one is causal system, but not memory system because this one depends on the past. But if we change it to like adding from minus infinite to infinite, for example, plus infinite. This one is not causal system because this plus infinite is future. This one depends on the future also. So this one is not causal. Make sense? I think you guys have a question, so questions. So you can think that causal has a more broader meaning. Memory is coming inside the causal most of the time, not always, because causal, past, present, not future. Memory is only present. Okay. So if you have my example, the final one, the first one is causal or not causal. From minus infinite to t. Integration of x from minus infinite to t. Is it causal or not? It's causal, right? Because it does not depend on the future. If you integrate up to t plus 1, that's not causal. The second example, minus infinite to infinite, this is not causal because it depends on the future. But both of them are not memoryless. They need a memory. Make sense? Okay. So let's go to one page above with another function called invertivity. Invertivity is straightforward. straightforward. Invertibility is like this. If you have a system having an input and having an output, say system A, if you have another system, say I don't know, tilde, that, so input is X, output is Y on this system. If you can find another system that input is Y, output is X, which is exactly inverse, then this system is called invertible system. Let's have an example. So, assume that we have y equals 2x in here. That's what the first example here. Y equals 2x. So we know that this y equals 2x. Assume that the output of second system as omega, and we want to have this omega output of second system to exactly the same to input to the first system to be invertible. To be invertible, we have to make this function. And we know that this y, we need some function of y, and we know that this y is 2 times x. What kind of system we can think to make this left side and right side are the same? We multiply by half. Multiply by half. So this y input to the second system is multiplied by half to be output of the second system. And we know that this y is 2x. So they cancel out. So we know that the output of the second system will be x, is same to the input to the first system. So we know that this y equals 2x system is invertible. We can find another system to make the output of the first system as an input and make them same to the input to the first system. That's the definition of invertible system. So when you're asked to judge this is invertible system or not, you will define the second system which can transfer the output of the first system to the input of the first system. If you find the second system like that, that's invertible. If you cannot find, or if you can judge, or if you can prove that there's no system like that, that's not an invertible system. What will be the example? If the system is xn, n is discrete time, y equals 0. And in this system, whatever input you apply, output is always 0. Can we go back? No, impossible, right? In case of such function, they are not invertible system. Okay? So we define memory system, invertible system, and causality. So let's talk about the stability. Stable is what? Stable is pretty, if you're standing on a hill, if you let's think about intuitive action. This ball is stable. This ball is stable. This ball is stable, right? So stable means if there is small input is given, that does not diverge. What does it mean? That means a system has always input and output. If you apply a small input, typically a force in this mechanical system, if you apply a small force, to this red ball, if you apply a small force, then their state changes. That's unstable system. In this one, if you apply a small force, they maybe rotate a little bit, but always go back to their neutral position. So there's a stable system. That means if you give a small input, that does not lead to diverging of the output. Diverging means what? They does not go back to their original position. In this one, if you apply small input, they go to here, but never go back to here. Of course, you can apply a big hit, and they bounce and maybe come back, but very little chance they go back to this position. They usually go back to like this. That's what they mean. And many stable systems involve energy dissipation, because when you go back to here, even though you apply small energy, if the energy does not dissipate, energy is conserved, for example, they always go back and forth continuously. So we sometimes need energy dissipation, typically damper or resistor, to find it. Time invariance system. So chapter 2, we have a linear time invariant system. So linear and time invariant are system property that define chapter 2 and most of this lecture. So time invariant, we define the first day of lecture, define that the behavior and characteristic of the system are fixed over time, meaning that does not change by time. So assume that we have a system. This is input to the system. This is output from the system. Assume that we have this triangular wave, and this shape will come out from the system. Assume that we apply this input after a certain delay. We change by time. We shift in time. So same shape, but shifted by time by t0. Even though we apply it, the same but shifted value will come out. So output doesn't change by time. That's our basic assumption when you do the experiment. When you measure certain circuit, even though you finish the lab today and come back 1 week later, our assumption is that the circuit works as before. Of course, that's not happens always. When you make a circuit, when you measure it, after 1 week later, we come back with it does not function as usual. It often happens in experiment, but our basic assumption is their value, their operation does not change by time. Whenever you when you operate it, they functions as usual. That's what we see in many of the experiments. Yeah, so this is a very typical assumption we have in engineering world. Example. Circuit again. Assume that we have fixed value of R, fixed value of C. Okay? When you apply your input as a current, output as a voltage, so input is current, output is a voltage. When input comes in, sometimes output come like that typically. If you delay the input, output will look like this. We know that, right? Assume that we have a time changing capacitance. If you learn more about the noise, something called noise, if you do the experiment in the circuit simulation, or not circuit simulation, if you do circuit measurement, like when you see the oscilloscope, the screen, you will see a wave, very pure wave, but sometimes you see something like this, right? You have the same experience. So this one is noise, either coming from your circuit, either coming from your device, either coming from experiment equipment. This noise changes by time always. This noise changes by time. So that means this one and this one may be different. Even though we apply the same signal, right? To make a sine wave, we apply the same signal. But this one and this one may be different. So there's not time embedded in the system. Another example is, assume that your capacitor is changed by time. It changed by time. Say this value of capacitor, they change from, say, plus 10 femtofarad to minus 10 femtofarad. In this case, when you apply a current here, this output will be different because our capacitance value changed. Right? In here, the capacitance value is 0. In here, the capacitance value is minus 10 femtofarad. Of course, there's not minus. Let me change. Sorry about that. What I'm talking about. So 20 femtofarad, 0 femtofarad in here. If you apply this current here, if you apply this current here, output voltage at here will be different from here because the capacitance in here is 20 femtofarad, and here there are 0 femtofarad. So this value will be different from 20 to 0. The output will be different, right? So if this capacitance changes, there's time invariant system, not time invariant system. They're time variant system. Okay. Questions, I thought. Okay. So this will be the last property we will talk. Linearity. You already learned about this in engineering mathematics 1 or 2, I think. So this linearity, how to judge linearity is superposition. Superposition is what? Superposition is defined as if we have certain function that there is a constant or scale factor of x1, x2, which is input. If you can do that in the way like this, meaning that we can separate the input to the system into output of the system, meaning that we have addition or subtraction at the input. If they come out from the system as output, adding of the output plus, that's one property. Second property is homogeneity, meaning that multiplication of the input, those multiplication can come out from the system That's homogeneity. If they meet both of them, we call them as, this one is called superposition principle. So let's have an example.